Hello everyone. Welcome back. This is in continuation to earlier video lectures on rock mechanics and static control. Okay. Today I'm going to discuss the following topics. Before I move on to new topics, okay, let me recap what we had covered in our what you call earlier video lectures. In earlier video lectures, we had discussed about what is Moore circuit and what are the various sign conventions that we use and the procedures to draw the Moore circuit. And apart from that, we had solved simple numerical problems on Moore circuit. Okay. Then we discussed about the Morse envelope. What exactly the Morse envelope is, as we know, like what you call the Morse circuits are drawn under various stress conditions. And if a common tangent is drawn to all the Morse circuits, okay, whatever the common tangent that we obtain, that is called Morse circuit. Okay, generally, it is not a straight line actually. I will assume that for our simplicity purpose, we'll assume that it's a straight line, but it is not straight line, it's a curve. Okay, it makes an what you call intercept. It makes an intercept on the y-axis, which basically determine what are the amount of intercept that will be obtained as part of Morse envelope. Morse envelope that represents the cohesive force that is acting along the failure plane. The intercept portion that indicates what the cohesion that will be acting along the failure plane, and whatever the angle made by the Morse envelope with the horizontal. Sorry, the angle made by the Morse envelope with horizontal is known as angle of internal friction, which basically represents how exactly the internal friction that will be acting around the failures. So this one, the using Morse envelope, will be in a position to determine like along the internal features that will be acting along the failure plane, such as the angle of internal friction and the cohesive forces. Then we discussed in detail about the stress distribution around the mine opening. Like under this topic, we discussed about narrow opening. Like in case of what you call board and pillar, the small opening that we made, how exactly the stress distribution is going to take place, and in case of wider opening, how exactly the stress distribution is going to take place, like in case of long wall mine. Okay, now let's move on. Now in this video lecture, we'll be discussing the leftover topics, like what as part of the second chapter, like relation between the lateral and vertical stresses and various numerical problems. Because see guys, the solving of application of what are the topics we discussed, that adds a lot of value to our learning curve. So we will as part of this video lecture, we'll be discussing, we are going to solve some numerical problems on what you call the computation of principal stresses, that has major and minor principal stresses, and what would be the what you call the maximum shear stress. Next, the normal and shear stress acting on a failure plane. Okay, and the last one is what you call different problems on Morse circle as well. So once we complete this part, then we will move on to the topics related to the third chapter, like physico-mechanical properties of the rock mass. And then once we cover the physico-mechanical properties, if time permits, then we'll discuss about simple numerical problems on porosity, void ratio, moisture content, degree of saturation, etc. Okay, let's move on. So what exactly the relation between the vertical stresses and horizontal stresses? Sorry. Let's see here what exactly is that. Second, let me draw this. Suppose let's say this is your block of rock mass. Okay, right. Let me choose a different color. Let's say this is a force which is acting like this. This one, sorry. Like this. Like this. So this part, this is called the vertical portion, right? So we'll call it as, I don't have sigma symbol, sigma v, sigma v. This is the same thing, the one which we discussed here. This is the vertical part of it, whereas this is the corresponding horizontal part of it, horizontal part of the lateral stresses. So, like in this case, there is a block of mass. The forces which are acting due to overlying strata are known as vertical stresses, and we need to compute what exactly the corresponding horizontal stress. And we are given the Poisson's ratio, like which basically determines the lateral strain to the longitudinal strain. This basically gives how exactly the deformation is going to take place in this particular block of rock mass due to application of vertical as well as the vertical horizontal forces. So the relation between them is going to be what? Sigma h is, which is nothing but the horizontal stress, equal to mu by 1 minus mu into sigma v. That's nothing but sigma h is nothing but the horizontal stress, which is equal to the horizontal or the lateral stress, which is equal to mu by 1 minus mu into sigma v. So here sigma h, as we discussed earlier, what we call sigma h is equal to horizontal stress, mu is equal to Poisson's ratio, and sigma v is what? The vertical stress. The vertical stress generally it will be due to it will be due to what? The presence of whatever the overlying strata that we have. Okay, because of that only the vertical stress will be acting on this particular or on a particular rock mass, mainly under mining conditions. Okay, now let's move on. Let us solve some simple problem on this, because in examination we might you might get questions on this. So let's see here. Now let us solve some problem, because since we know the relation between the horizontal stress and the vertical stress. Okay, sigma h is the horizontal stress that is equal to mu by 1 minus mu into sigma v, where mu is Poisson's ratio and sigma v is the vertical stress. Now let us see what exactly this problem. Given the vertical stress acting on a small opening, small opening, sigma v is 30 megapascals. Find the corresponding horizontal stress, and we are given the vertical. The value of Poisson's ratio is how much? Mu is equal to 0.75, and we are asked to find out what is the corresponding horizontal stress. So the sigma h that we need to find out, and the sigma v is the vertical stress, which is equal to 30 megapascal, and mu is equal to 0.75. So sigma h is equal to mu by 1 minus mu into sigma v, where mu is 0.75 by 1 minus 0.75. That's nothing but 0.25 into 30. So this is going to be what? 25, 25, 3. Yeah. So 3 into 3, 3 into 30 is 90. So it's going to be 90 megapascal. So these kind of simple problems you might come across in examination. Okay? Similar kind of thing. Next one, let's move on. Okay. So now let us solve some more problems on the stresses that are acting on a block of 2D block of rock mass. Okay, the numerical problems see in this section numerical problems in determination of normal and shear stress along the failure planes. Okay, see for the given state of stress in 2D block diagram. Okay, here there are two stresses. The horizontal one is which is of tensile nature or 50 megapascal, and the vertical one which is of 10 megapascals. So the 40 megapascal is what? This is a kind of what you call shear force that will be acting along various planes. Now here, if you look at 10 megapascal is compressive, and which is a vertical one, And whereas the on the along the lateral direction of the horizontal direction, the force, the stress is of what? Tensile nature. So as per the sign convention, what are the sign convention that we follow in computation of the principal and major and minor principal stresses? Okay, mainly the compressive, if the forces or if the stress, the compressive forces, the force is of compressive nature, then we'll take it as negative. If the force is of what you call tensile nature, we'll take it as positive. Okay, I repeat, if the force acting, what you call force is acting, vertical force or the normal force which is of compressive nature, we'll take this one as negative. And if it is of what tensile nature, we'll take it as a positive. Next, if the what you call shear force, if it is acting along the clockwise direction, if it is known as what you call, it will be taken as positive. If it is acting in anti-clockwise direction, then it will be taken as negative. So in this case, the sigma x, the one which is acting like this is of what tensile nature, which is going to be positive. Whereas sigma y, the force, the normal force which is acting along y direction, that is of 10 megapascal, and it is of what? Compressive nature. The sign convention that we'll take for this one is negative. Okay, if the 40 megapascal, whatever the shear stress that is acting, if it is of clockwise direction, then it is taken as positive. If it is counterclockwise, then it is taken as negative. So given this what you call the state of stress and a 2D block diagram, you are asked to find out what you call major principal stress, minor principal stress, and angle of principal plane. So where exactly it is going to be played, what is the maximum value, what is its minimum value, and what would be the angle of that particular plane, that we need to find out. Like it might fail something like this, so we need to find out that kind of thing. So what exactly this angle is, how much is the vertical, the narrow vertical major stress and the minor principal stress, how much is the angle of this, that we need to find out. Okay, let's see how exactly it is. Let me clear this. Okay, we are after to find out this. Okay, one is 40, 50, right? Okay, yeah, same diagram. Okay, see here sigma x is taken as positive because it is of tensile. As I said, once again I'll repeat the sign convention that we follow. Okay, what you call while solving these kind of problems, like the forces or the stresses which are acting in a block of 2D model, a 2D block of rock mass. Okay, if it is of tensile, the normal stress, if it is of tensile nature, it is taken as positive, and if it is of compressive nature, it will be taken as negative. Here, the normal stress acting along x direction is of what? Tensile nature, so plus. So sigma x is equal to plus 50 megapascals. The sigma y, as I said, it is of compressive nature. It is taken as negative. So nothing but minus 10 megapascals. Since this is acting on the clockwise direction, right? This is acting on this one clockwise direction because this is what exactly it caused some deformation there. So clockwise direction. So it is tau xy. It is taken as what? 40 megapascals. So we know the angle made by the failure plane. The formula for this is tan 2 theta is equal to 2 tau xy by sigma x minus sigma y. So 2 into tau xy is how much? 40, right? Sigma x is how much? Plus 50, right? Minus of sigma y is nothing but minus 10. Minus of minus, this is going to be plus. So 80 by 60. So this is what the angle that will be hitting it. Okay. Next, we need to find out the principal stress value. Okay, either maximum or minimum. Look at here, the formula for this one is sigma max or minimum. The maximum indicates the maximum principal stress and min indicates the minimum principal stress. So in this formula, if you look at here, sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy whole square. So if you look at here, in this formula, the plus sign represents the value that we are going to determine now using this equation is going to be maximum. If I use the negative term, then the value that I'm going to get it is of minimum. That's all. So in order to get the maximum value, we'll be using the plus sign, and to get the negative, that's what exactly. And to get the negative value, then we'll be using minus sign. So 20 plus or minus square root upon substituting these values into this. Okay, this is what exactly we got it. Sigma max is equal to 20 plus 50, which is equal to 70. Whereas 20 minus 50, this is minimum. This is going to be how much? This is of what you call. See, this is of tensile nature, whereas this is of what? Compressive nature. That's why you got what do you call? Here you got the positive. So if the normal stress is of positive, then it is called is of tensile nature, and the minimum value it is of compressive nature. That's what exactly need to sign indicates. Okay, and this is how we need to solve. So just to reiterate, basically you are given a what you call the a 2D block of rock mass in which the normal stresses and the corresponding shear stresses acting, and you are asked to find out what is the what you call the angle made by the failure plane in which there will be maximum and minimum normal stresses that are acting on it. So in order to compute the angle, this is what the formula. You have to calculate the maximum value that is acting on the maximum value of normal stress acting on the plane of failure is known as major principal stress, and minimum value is known as minor principal stress, and that particular plane of failure is known as principal plane. Okay, hope you understand this. Next one, the second question. The state of stress at a certain point in a stressor body is as shown in the figure. Okay, this is it's a 2D block of this one. This is of compressive and this is of vertical tensile. Right. The normal stress in x direction is 80 megapascal, which is of tensile, right? And the y direction is 40 megapascal, which is of compressive. Calculate the radius of the motion. Okay, quite interesting. Look at here. So, see, look at here. In this block of mass, only the what you call the sides of this block or on the edges of the block, only the normal stresses are acting. There is no shear stresses. Nothing but if in the absence of shear stress, the normal stresses that are acting, they are known as what? Principal stresses. That's what exactly it is. So here we are not being provided with the shear stress value. The shear stress value is present, then we need to use what? Now to calculate the major and minor principal stresses, we need to use this formula. We need to use this formula because here the shear stresses are present. But if in the next problem, basically in the 2D block, only the normal stresses are acting, but the corresponding shear stresses are missing. So that indicates what? Well, the normal stresses which are acting on that particular plane, they are of what? Principals. They are of maximum, either maximum or minimum, which is nothing but the major principal stress and the minor principal stress. So from this diagram, we can easily say that the sigma x is nothing but because that is the maximum one. So which is of major. So major principal stress value sigma x, sigma 1 is equal to 80 megapascal, and a minor principal stress. See here in the sigma x is of tensile nature. We'll take this as a positive, and the sigma y is of what? How much? It is of what compressive nature. We'll take this one as negative. So your curve is going to be something like this. Okay, let me draw this here. It is going to be something like this, and this is one value is 40, so this is somewhere here. It is 40. This is of 80. This is somewhere here. If we draw this here, because if I take the sine curve, sorry. Okay, this value is how much? 40. This value is how much? 80. Now, how exactly our circle is going to be? Our circle is going to be pass through this. Should be dragged like this. So it should come something like this here. Okay, it should pass us through this. So this is how it's going to be. So I need to set up it, and you are asked to find out what is the radius of the Mohr circle. Radius is nothing but what? See, up from this is 0. From this is going to be 40. And from this is because these are vertical. See here, there are, as I said, there are no shear stresses. That's why the sigma x itself the major principal stress and the sigma y itself a minor principal stress. That's what it is. So yeah, from origin to toward this side is my 40 and this is 80. So 80 plus 40 is how much? 120. 120 by 2 half of this. That's going to be a circuit. That's going to be this. This is going to be a radius. So that you need to find out. So 80 plus 40 is 120. 120 by 2 is 60. 60 is going to be a radius of mass. So this is a very pretty simple formula, a pretty simple problem. Only thing is you need to understand what exactly you need to understand this diagram. Since there are no what you call the shear stresses acting on this. So what are the normal stresses that are given? That they itself indicate thereof for what? For stresses. Okay, let's see the solution of it. Next, move on. Let's move on. Okay, look at here. In the above diagram, all along surface x and y, there are no shear forces acting on it. Hence, the normal forces acting on them, okay, is actually so on them is also known as principal stresses. Okay, here sigma 1 is nothing but sigma x is equal to 85, which is a positive tensile nature. Sigma 3, there's nothing but sigma y, which is equal to 40 megapascal, which is of compressive nature. And the radius of most circle is equal to as I said, right? This is 40 and this is 80, 80 plus 40 because that's a total together 180. That's what it is. 180 by 2 is nothing but 60. So this is not the formula. So if you look at the formula wise, radius is equal to sigma 1 minus radius of most circle sigma 1 minus sigma 3 by 2. Okay, here we got on the other side we have got negative of it. So minus of minus is equal to plus. That's why you got it 80 plus 40 is equal to 120 by 2 is equal to 60. So this is how exactly it is. Okay, so let's move on. Okay, this is the third problem. Okay, this third problem, the stresses acting on a 2D and a 2D block of rock mass is represented by the following diagram. The same as the top for this one. Look at here. Calculate the major and minor principal stresses. That's what he was asking. So how to get it now? So the stresses which is acting, this is of compressive nature. So then definitely the sigma x is equal to. See here, these are not the principal stresses. Why? Because the normal stress is associated with the corresponding shear stress as well. The shear stress as well. That's why they are not. In the earlier case, there are only the normal stresses in the earlier problem. So that's why we straight away we took them as what we call the principal stresses. Because in the absence of shear stress, the normal stress itself is principal stress. Here, this is a 40, which is of compressive nature. That's why the sign convention is minus 40. And this is a vertical 70, which is acting along y-axis or along y direction, 70 megapascals. Okay, tau xy, this is acting 50 megapascal. This is acting along counterclockwise direction. So counterclockwise is a minus 37. So upon substituting this, okay, same formula which we used earlier. Okay, so let's see from the above formula, sigma x is equal to which is of compressive nature, minus 40, sigma y is equal to 70, and the tau xy, so the minus because it is of counterclockwise direction, and we need to substitute those things into this formula. Sigma x plus sigma y by 2, and the major principal formula for major principal is equal to sigma x sigma y by 2 plus 1 by 2 into. Earlier the formula was a bit different. Like it's the same formula. Only thing is we have taken these 1 by 2 towards inside. Okay, if I take it outside, then it's 1 by 2 square root of sigma x minus sigma y whole square plus the 4 tau xy whole square. So same way here the negative sign. The plus sign indicates the major value and minus 1 indicates minor value. So the upon substituting the above values, the major and minor principal stresses are major principal stress is equal to, if I substitute these values, the value that I'm going to get is 89.3 and the minor is this one. So this plus sign indicates what it is of what you call tensile nature. Negative sign indicates what it is of what you call compressive nature. Okay, let's move on. Next, okay, that is about anything. Yeah, I've covered the 3 problems so far. Fourth problem. The major principal stress, sigma 1 and the minor principal sigma 3 acting in a block of rock mass is given by 10 megapascal, 4 megapascal respectively. There's nothing but sigma 1 is equal to 10 megapascal and the sigma 3 is equal to 4 megapascal. Calculate the center of the Mohr circuit. What exactly is this? Let's see. We draw this diagram here. Here both the values are positive. So it's something like this is how we got it, just for the time. Okay. Now, see it touches this one, right? So minor principal stress is nothing but what? This value is for how much? 4 megapascals. Okay. And this value is how much? 10 megapascal. Look at here. So this 4 megapascal up to from origin to this 4, and from origin to this is 10. Okay. So now what happened? 10 minus 4, this part. But I need to find out, okay, here it is not radius. Here we are asked to find out the center of the Mohr circle. Is nothing but this part I wanted to find. This I want. So how much it is going to be now? So how to get this value? This is sigma 3. This is what? Sigma 1. From this to this. Let me check this. From this to this. This value is how much? Sigma 1. This is sigma 1. Whereas this is what? Sigma 3. From this to this. This is sigma 3. Okay. Sigma 1 minus sigma 3 will give this portion. Okay. And so sigma 1 minus sigma 3, half of this will give me the radius. That's what we discussed earlier. Sigma 1 minus sigma 3 by 2. But I need to get this one, right? Sigma 1 minus sigma 3 by 2 plus sigma 3. This part I need to add because my coordinate starts from to this part. So sigma 3 plus sigma 1 minus sigma 3 by 2. If I solve that, the result is going to be how much? Sigma 1 plus sigma 3 by 2. I repeat, here to find out the center of the Mohr circle, what I should do now? This point represents sigma 3, which is of minor principal stress, and this point represents sigma 1, which is of major principal stress. Sigma 1 minus sigma 3 will give this diameter of what you call the Mohr circle. Sigma 1 minus sigma 3. Okay, and half of that will give the radius. Like sigma 1 minus sigma 3 by 2 is this part, I got it. But to this, I need to add this one because my coordinate has to, it will be counting the coordinate of any point from the origin, right? With respect to origin that we need to compute it. So from this one, how much it is going to be? This part is sigma 1 minus sigma 3 by 2, this portion, plus sigma 3. Okay, if I solve this, the value that I'm going to is sigma 1 plus sigma 3 by 2. That's it. That is what it is. And the y-axis is going to be what? Is 0. Right? Remember, and substituting these values, 10 plus 4 by 2, comma 0. 10 plus 14 by 2 is 7, comma 0. This is what the center of the Mohr circle is. These are the simple numerical problems that we might come across in the examination. Okay, so hope you understand this. Try to concentrate on this. This is somewhat what you call tricky problem, but still it is worth of knowing it. Okay, sometimes we may come across this kind of problem. It is something like that. So far, what we did is see here in this block of 2D block of rock mass, there are different stresses acting. One is called this is of what you call along horizontal direction. Okay, this is of what you call vertical direction. So the horizontal direction, the forces, the normal stresses are of what? They are acting towards inside. There's something they are of compressive nature. They are acting away from the body. They are of tensile nature. So compressive will take them as a negative, and the vertical tensile will take them as positive. And these are all what? The corresponding shear stress acting on each surface of 25 megapascals. So the horizontal stress is of 80 megapascal and vertical is of, which is of tensile nature. That is of vertical how much? 50 megapascal. And the next one is this shear stress is how much? 25 megapascals. So now it might fail at some place. Now I wanted to find out what would be the what you call the normal stress. Wanted to find out. Okay, see, determine the stress acting, because it might, we don't know in like in which plane it's the what you call the block of mass is going to fail. But I wanted to find out the corresponding normal strength and the shear stress acting on a plane which makes an angle of how much, 30 degrees in clockwise direction. Okay, generally if angle is of towards clockwise direction, that will take it as a negative. If it is of anti-clockwise direction angle, that will take it as a positive angle. I'm talking about this. Okay, so now we need to find out what you call the normal stresses. One second. These are called normal stresses. The corresponding shear stress like this. So we need to find out along this failure plane what would be the corresponding. Let's say this is theta, so this is going to be sigma theta. We need to find out what is the value of sigma theta, normal stress acting along the failure plane, and the corresponding tau. There is nothing but a shear stress acting along the failure plane. There's nothing but tau theta. This is what exactly we need to find out. Okay, let's see. Take this one. Look at here. So this is what it is. So as I said, sigma x, which is of compressive nature, minus sigma y, and tau x, which is of anti-clockwise direction, I took it as negative. And as I said, if the angle is of vertically, as mentioned, it is counter-clockwise direction, we take it as negative. So minus 30. So this is the formula that we will be using to calculate the normal stress that is acting between numerical as to transformation equations, sigma x, sigma y, and the corresponding theta value. If I put it, this is what the value I got it. So it is which is equal to, which is of negative. Negative is nothing but it is of compressive nature. Okay. Next, let us find out what is the corresponding what you call shear stress. So this is the formula for shear stress is this much minus, look at here, the formula for the normal stress acting along the failure plane is sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sin 2 theta plus tau xy into sin 2 theta. So here sigma theta is equal to sigma x is nothing but it is of what compressive nature minus 80, and this is of tensile nature. Obviously, we follow the sign convention. This is a minus 80, and this is minus of since this is positive minus 50 by 2. The cos 2 into theta is nothing but minus 30 degrees because it is of clockwise direction, and the minus 25 into sin 2 of how much, minus 30 degrees. So upon solving this what do you call this equation, the value that we got is minus 25.9 megapascals, which is a normal stress. Negative sign indicates it is of compressive nature, which is of normal stress acting on a plane which makes an angle of theta. Okay. Next, we need to let's find out what would be the corresponding shear stress. The formula for formula to calculate the shear stress on a plane which makes an angle theta is equal to, okay. Generally, in some books it is because this sign convention, if I interchange them, this sign convention will go off. In some books, it will generally they'll follow it something like sigma y minus sigma x by 2. Nothing but it's just interchanging of these two terms, so that there is no need to write for you to write explicitly the negative sign. Okay, so here minus of sigma x minus sigma y by 2 into cos sin 2 theta plus tau xy into cos 2 theta. So this is of compressive nature, so minus 80 this one, and it is of clockwise direction, so minus 30 degrees, and this is of what you call a tau xy, which is of counterclockwise direction. So I took it up, this one minus 25. Okay, and cos 2 of minus 30 degrees, the value which we got in this one. Again, this is of what compressive, and this is of what you call compressive nature. So nothing but this is acting in the, here in this case it is acting in the opposite direction. That's what exactly is negative sign indicates. Okay, so One is the vertical normal stress acting along the failure plane, and the second one is the corresponding shear stress acting along the failure plane. So these two formulas we'll be using to solve the normal and shear stresses acting on any plane. Okay, so that with that, like, we'll be done with the second chapter. Now let's move on to the third chapter. This chapter is very, very important. In this, basically, see, so far what we had discussed. We discussed about the stresses, strains, okay, how exactly the stress redistribution that's going to take place, and what are different models of elasticity, what is the relation between them, and the simple numerical problems on them. Next, let's move. What is what we call rock burst, coal bumps? What are the causes? Preventive measures. Next, we discussed about how exactly the stress distribution is going to take place in a 2D, two-dimensional block, and three-dimensional block, and how to draw the Mohr circle of it, and what are the different form. Next one, what is principal plane? What is major principal stress? What is minor principal stress? What is shear stress? And how to there are different formulas. Next we discussed about what the normal stress and shear stress is acting along the failure plane, which makes an angle theta, just a few minutes back, which we discussed. Then we discussed about how to draw the Mohr circle and what are the sign culture that we'll be using to draw the Mohr circle, and what you call given different values, how to compute various other values from the Mohr circle. Okay, and the simple numerical problems on all those concepts we have discussed. Okay, now let's move on. Physico-mechanical properties. The term itself indicates what exactly we are going to study. Physical, nothing but the properties of a rock mass which are of physical in nature, which appear. Suppose, let's say, if we take any human being, any person, let's say, okay, what would be the height? What would be the weight? What would be the what you call the color? Something like this. So these are the properties of a human being. Like we can distinguish them by seeing by their physical appearance. Physical appearance. In the same way, here also, in case of properties of, while studying the properties of rock mass, those properties which we can determine by analyzing their physical nature, by seeing that, okay, what are the properties that we can measure? Those properties are known as physical properties. Those properties are known as physical properties. Mechanical properties are those properties of rock mass are those properties which can be determined in the laboratory, which requires some kind of testing in the laboratory to analyze its behavior. For example, let's say compressive strength, tensile strength. So by seeing that, we can say, by seeing the rock mass itself, we cannot predict how much is the strength or how much is the load it is going to bear, and what would be the strength of it. So we cannot do that unless until we test them in the laboratory. In the same way, by those properties of rock mass, which can be determined or which can be assessed to a certain extent by its observing its physical nature. So those properties are called physical properties, guys. Look at here. The following are the various physical properties of the rock mass, like what you call density, bulk density, specific gravity. I'll discuss one by one in the next coming slides. Okay, density, bulk density, specific gravity, porosity, void ratio, water content, permeability, degree of saturation, thermal conductivity, and electrical conductivity. Total 10. Okay, repeat: density, bulk density, specific gravity, porosity, void ratio, water content, permeability, degree of saturation, thermal conductivity, and electrical conductivity. So let's move on. Next, those are all what you call physical properties. Next, mechanical properties. As I said, these are all the what you call strength indices, like which basically given the physical strength of the rock mass, like compressive strength. Under compressive strength, again, there are two types. What kind of stress? Anyway, guys, these topics we are going to discuss in the coming videos or coming lectures in detail. Okay. For now, let's try to understand that. Compressive strength or nothing but uniaxial. Under that, uniaxial compressive strength or unconfined compressive strength. Next, confined compressive strength or triaxial test. Next, these two are subcategories of compressive strength. Next one is shear strength. Then under shear strength, again what? A single shear, double shear, punch shear, and oblique shear test. These are the shear test. Next one, tensile strength. See, we cannot measure. There are different methods again under that. Direct method of tensile strength, indirect method. Indirect method is also, this is very important from examination. That is also known as Brazilian test. Okay. Next, like we'll discuss about what you call the next mechanical properties: slack durability index, point load strength index, proto diagnose strength index. So these are all what you call various mechanical properties, and these are all what you call the physical properties of rock mass. Let us discuss the physical properties now. So we can say here by what you call, by holding any rock of what you call any rock mass in hand, you can simply say that whether it is of lightweight or what you call heavyweight, right? So we can, because by, that's why it is called the physical property. By seeing that, like by holding it, we can say okay, it can what you call float on water, and it can what you call it can submerge in the water, right? So what exactly the density now? Density, it is the ratio of mass of rock sample to its volume. So density is nothing but density rho is equal to, it is denoted by symbol rho, is equal to m by v. Okay, so the mass is different and weight is different, guys. If the mass multiplied by gravity, then we'll get the weight. Mass, the units for the mass is what you call kgs, whereas the what you call units for the weight is newtons, because we are going to multiply with the gravity. That's what it is. Okay, so the density is nothing but it's a ratio of mass of the rock sample, small m, to its volume v. So density rho is equal to m by v. Next, bulk density gamma. It is the ratio of weight. See, here it is mass and here it is weight. Weight W, capital W of rock sample to the total volume of the sample. Total volume nothing but capital V. So bulk density is gamma is equal to W by V. We know that like the weight is equal to what? Mass into gravity, right? If the mass multiplied with gravity, then we'll get the weight, right? This one. Okay. M into mass into gravity. Now look at here. M by V, that will get what? Density, right? If I say replace this M by V, I can replace with what? Rho into G. That's what exactly it is. So this is what exactly the relation between bulk density versus density. So I repeat, guys, this is very, very important. Most of the people gets confused what exactly the difference between them. See, in case of density, rho, it is the ratio of mass of the rock sample, small amount, just mass, which is in kgs, which will be measured in kgs, to its volume, capital V. Density rho is equal to m by v, where m is in mass in kgs. Now coming to the bulk density gamma, it is the ratio of total weight. Weight is nothing but what? Mass into gravity is weight. Weight W of the rock sample to the total volume, capital V, right? So bulk density gamma is equal to W by capital V. What is W now? Mass into gravity, right? So m by v, we know what exactly this one? M by e is density. So I'll substitute this one here. So bulk density is nothing but what? If I what is the density of rock mass that will be getting? If I multiply that with the acceleration due to gravity, then the value that I will be getting is of bulk density. Okay. Next, dry unit weight. See here, because whatever the rock mass, if it contains what, it might contain what? Some water in that. Okay, it contains some porous medium in that, or it might contain some voids in that. Okay, it might contain some portion will be occupied with the solid mass. Okay, now we need to find out what is dry unit weight. It is the ratio of weight of the solids to the total volume, guys. This is very important. Here we are taking total volume, weight of the solids, solid portion to the total volume, capital V. That is what exactly the dry unit weight, sigma D. Okay, here total volume, guys. Remember that. Why I'm stressing on this will be knowing in the coming slides. Okay. Okay. Next one, unit weight of solids, gamma S. The previous one was, earlier one was what? Gamma D. Now this is gamma S. It is the ratio of weight of the solid to the volume of solid. That's what it is. Weight of the solid to the volume of solid. This is called unit weight of solid. Unit weight of solid. Look at here. Let's move on to the previous one. Look at here. Dry unit weight is nothing but weight of solid by total volume. Now unit weight of solid, because this is denoted by gamma D. Okay, and the bulk density is nothing but what? Total weight by total volume. Okay, and dry unit weight gamma d is equal to what? Weight of solid by total volume. Okay, once again I'm emphasizing this, here it is total volume, whereas unit weight of solid is gamma s is equal to what? Weight of solid by weight of volume, whereas in case of dry unit weight it is how much? Gamma d is equal to weight of solid by total volume. This part makes it. Okay, next, what is specific gravity? It is the ratio of unit weight of solid to the unit weight of water, because we are comparing with respect to water. So unit weight of water, solid, to the unit weight of water. This ratio is called, what is unit weight of solid? Unit weight of solid nothing but weight of the solid by volume of the solid. This is what exactly the unit weight of solid. Okay, this is what the unit weight of water. It's the ratio of unit weight of solid to the unit weight of water. So capital G is specific gravity, capital G is equal to gamma S unit weight of solid by gamma W unit weight of water. Okay, now let us discuss this concept. This is very important concept, guys. Porosity, void ratio, and how to find the relation between them. Okay, let me explain in detail this diagram. Let us say this is one heap of what you call rock sample that I am having. Look at here, it contains what? So many grains in that. Okay, small boulders, big boulders, and there are some gaps in that. Okay, there are some gaps in that. So I can represent this one like this way. Like if I crush everything, so this is the total volume that it has occupied. Right? That's what exactly. I will assume that. In that, if I crush it, right, only certain portion will be solid. Okay, certain portion will be void. If it contains voids, it's going to be air or void. Or what do you call? If it contains what you call water in that, inside that, if it contains some water in that, like water generally it will be occupied by the void portion, right? So that void portion again not only air, it also contains water and what you call volume of solid, all put together, complete volume. That's nothing but, let me reiterate it. Here this diagram basically represents, let us say the total volume of the sample is V, capital V. Okay, I'll divide the total volume into the following subparts of it. One is the Vs is nothing but, sorry, this is something wrong here. Vs is nothing, this must be something. Okay, Vs is nothing but the volume out of this total volume. What should be the solid portion of it? And the remaining portion, if it is of dry one, right? What should be the remaining portion is going to be what? Solid. If I remove the solid portion, remaining portion is void. That is the empty portion that is present between the what you call the grains of this sample. Am I right? So that is the volume of void. This one. Okay. And again, this volume of void is again further subdivided because it might contain some water in that. So if certain portion of the void contains water, then we need to find out what, okay, this much water is present in the void portion. And if this portion doesn't contain anything, it's a simply particle just like that, it was kept open. Nothing but it contains air. So this is volume of, sorry, it's volume of air. So the volume of air plus volume of water, both are put together. Both are put together is known as volume of void, and this is volume of solid. So volume of solid plus volume of void is going to be all put together. How much? It's going to be total volume. Total volume. Now coming to the what you call analyzing the same concept in terms of weight. Okay. Obviously, air doesn't contain. It will not be having any weight. We are just ignoring that. So weight is nothing. Weight of the sample is nothing but what? Weight of the solid part plus weight of the water. If it contains some water, it's going to be this. So total weight is capital W. Under that, see this much portion is the solid part, right? Volume of solid. So this much portion, if I weight, I will be getting what? Weight of the solid. Okay, and this much, if it contains some water, this much portion, because this much portion is the volume of void, right? So it's I'm going to get what? Weight of the water. So weight of the solid plus weight of the water put together, total weight. Okay, this is what exactly the analogy of this particular diagram. Okay, let us discuss now. If you understand this, it will be very easy. Okay, the next concepts are going to be very easy. What is porosity? Porosity n, small n, is equal to, it is the ratio of, because it is the ratio of volume of void. How much is the volume of void to the total volume of the sample? See, if you like some sponge kind of thing, some cane kind of thing, it is a porous one, right? We'll simply see, okay, this is the total value, out of which it is a very porous. It contains some wide portion in that. So we can say, like, by seeing the rock sample, if it contains small holes in that, we can say it is a very porous one, right? So because based on the porosity only, if the same rock sample present somewhere in the what you call the ground, okay, below the earth crust, what happens? It's quite possible if there is any water table, right? Water might what you call will pass through the porous portion, right? So the permeability of the rock mass, nothing but the flow of water through the rock mass is being determined, is being based on the porosity of the rock mass. Now, what exactly the porosity is? Porosity, it is denoted by small n. Is equal to, it is the ratio of volume of void to the total volume of the rock sample. So porosity n is equal to volume of void by total volume V. Next, void ratio E. It is the ratio of volume of void, see, the numerator is same, to the volume of solid of the sample. This is called void ratio. I repeat, porosity is equal to, small n is equal to volume of void by total volume. Whereas the void ratio, small e, is equal to volume of void by volume of solid. Now, let us find out the relation between them. Simple. Look at here. Porosity n is equal to, okay, volume of void by, how to find out this one? Find out the relation between them. That's what exactly, right? Relation between porosity and void ratio. N is equal to volume of void by total volume. So this volume of void, I can write it. Yeah, the total volume is nothing but what? Volume of solid plus volume of void, right? So I can subdivide this, what you call, I can rewrite this total volume as what? Volume of void plus volume of solid, which is nothing but total volume, right? Same thing I did here. So total volume is equal to volume of void, volume of solid plus volume of void. Okay, divide both, what you call, numerator and denominator with what you call volume of solid. Here in this case, he took what you call inverse of it. So 1 by m is equal to what? This I took it here, and then divide it. Divide with what you call volume of void. It's just a reciprocal of it, so there's nothing. It's just simple reverse of this, and divide with what? Volume of void. So we got this. But what we know, volume of void by volume of solid is nothing but, the reverse of it is nothing but your void ratio. That's why you got 1 by. Okay, if I rearrange them, 1 plus E by E. If I rearrange them, N is equal to E by 1 plus E. This is what the relation, nothing but porosity N is equal to void ratio E by 1 plus E. This is what exactly the relation between particle porosity and void ratio. Okay, let us see. Yeah, this is what a few minutes back which we discussed. What is water content or moisture content? This is another important terminal, what you call, definition that we generally come across. Okay, while discussing the behavior of the rock mass. How much is the moisture content in that? So what is exactly this one? Water content or moisture content, small w, is the ratio of weight of water to the weight of the solid expressed in percentage. Yes, we discussed in the earlier slides, right? Yeah. Weight of solid to the this one. Weight of solid portion is this. If I measure the solid portion, it is going to be weight of the solid. This is weight of the water. Okay, let's come back. It's a ratio of what? Weight of water to the weight of the solid, expressed in percentage. Percentage nothing but multiplied by 100. So this ratio is called water content or moisture content. Next, let us discuss what is permeability now. So it is a property of rock sample, which is a measure of amount of water flowing through it. How much is the water? How much is the water flowing through that? Okay, it depends on the porosity and void ratio of the sample. Okay, how freely if the given rock sample, how free is the water? If there is a water table, how exactly the water, what you call, will flow through that particular rock sample. Okay, the porosity of the sample is measured by Darcy's law. So what exactly it is? The quantity of water, this is very, very, very important, this formula. The quantity of water Q flowing through the sample is given by Q is equal to KIA, Kia. Okay, Kia. So where Q is equal to quantity of water flowing through the sample rock mass in cubic meter per second. Okay. I is equal to hydraulic gradient. What exactly is the hydraulic gradient now? Hydraulic gradient is nothing but there is a water table. Suppose your water table is something like this. So here it is of gradient is this much, and here in water pressure is like this. And it is what do you call, the water is flowing like this. It's flowing like this. So this vertical level difference, this is called hydraulic gradient now. Let's say this is H1, this is H2. So H1 minus H2 by over this length, because let's say this is point A and this is point B, and this is of H1 height, this is of height H2. H1 minus H2 over this length, that will give the gradient, hydraulic gradient. I repeat, look at here, this is of what? Just a minute. H1. Okay. This is of what? H2. This entire length is how much? Let's say this is capital L. Yeah. That's what it is. So this is at a higher gradient and this is at a lower gradient. H1 minus H2 over a length what? L. So that will give your value of I. Sometimes, you know, in problems they might not given what exactly the value of hydraulic gradient. They might have given, okay, the water is flowing at this particular, at this one, this is what the hydraulic pressure of it. This is what the hydraulic pressure of it. And this is the length distance between these two boreholes or whatever it is. This is one borehole and this is another borehole. This is what the hydraulic pressure here. This is what the hydraulic pressure here. Okay, height H1 and H2, and the distance between these two boreholes. Then you are asked to calculate what would the corresponding hydraulic gradient. So H1 minus H2 divided by the length, that will give the hydraulic gradient. And A is the cross-sectional area. Whatever the rock sample that we have, what should be, that is flowing through that. So how much should be the cross-sectional area of that? So the permeability, which is a measure of the quantity of water flowing through it. So the quantity of water Q is equal to Ki into A, where Q is equal to quantity of water flowing through the rock mass in cubic meter per second, and I is the hydraulic gradient. I explained this one again earlier. Okay, the A is the area of cross section or the cross sectional area. Okay, so let's move on. This is about permeability. Next one, let us discuss about what you call degree of saturation. Okay, it is the ratio of degree of saturation, because if any rock mass contains full water, we can say it is fully saturated, right? If it doesn't contain any water, we'll say it is dry. Am I right? The same way here also, what you call degree of saturation. It is the ratio of volume of water to the volume of void expressed in percentage. So the degree of saturation capital S is equal to volume of water by volume of void multiplied by 100. Okay. So now there are two conditions. Either it is fully saturated condition or dry condition. So in case of fully saturated condition, obviously what happens? The complete vacant portion or the void portion is being filled with water. There won't be any void. So volume of void is equal to how much? Completely filled with water. So volume of water. So if I substitute instead of volume of void, volume of water, volume of gets cancelled. How much is the value? It's going to be 100%. That's what it is. Next, under dry condition nothing but it won't contain any water in that. So volume of water is going to be how much? It is going to be 0. So if I substitute the value of 0 by something, it's going to be 0. So the degree of saturation in case of dry condition is 0%. In case of fully saturation, it is how much? 100%. So this is what it is. I repeat, the degree of saturation capital S is equal to, it is the ratio of volume of water to the volume of void expressed in percentage, nothing but multiplied by 100. So under fully saturated condition, the value of S is equal to 100%, and what you can under dry condition, the value of S is equal to 0%. Okay, so let's move on. Next, the leftover two physical properties are thermal conductivity and electrical conductivity. So what exactly is thermal conductivity? Because see, in underground mines, if you go deep and deeper, right, there will be what you call heat and humid conditions. Because rock mass gets heated, or its temperature gets increased, because the rock mass is present at a greater. So we need to understand, like, okay, what would be the what you call the thermal conductivity of the rock mass? Because whatever the air that is flowing through the opening or flowing through the mine workings, okay, how much what you call the heat is being what you call carried by that particular what you call air, or how much will be the what you call the transmission of heat through the rock mass. So that is another property. It indicates the transmission of heat through the rock mass. The coefficient of thermal conductivity depends on what? The properties of the rock mass and its composition. If the rock mass contains any metallic properties, then its thermal conductivity increases. That's what it is. Okay. Next, coming to the electrical conductivity. This is another property. The property of rock mass indicates the electrical conductivity through it. So these are all what you call various various properties of it. This. Okay. Yeah. With this, I'll conclude this video lecture. Thank you. Thank you very much.